either on a magnetic needle placed at A or on an element of current at A. Five, induction. We know that the discovery of electrodynamical induction followed not long after the immortal work of Ampere. As long as it is only a question of closed currents, there is no difficulty, and Helmholtz has even remarked that the principle of conservation of energy is sufficient for us to deduce the laws of induction from the electrodynamical laws of Ampere, but on the condition, as Bertrand has shown, that we make a certain number of hypotheses. The same principle again enables this deduction to be made in the case of open currents, although the result cannot be tested by experiment, since such currents cannot be produced. If we wish to compare this method of analysis with Ampere's theorem on open currents, we get results which are calculated to surprise us. In the first place, induction cannot be deduced from the variation of the magnetic field by the well-known formula of scientists and practical men. In fact, as I have said, properly speaking, there is no magnetic field. But further, if a circuit C is subjected to the induction of a variable voltaic system S, and if this system S is displaced and deformed in any way whatever, so that the intensity of the currents of the system varies according to any law whatever, then so long as after these variations the system eventually returns to its initial position, it seems natural to suppose that the mean electromotive force induced in the current C is zero. This is true if the circuit C is closed, and if the system S only contains closed currents. It is no longer true if we accept the theory of Ampere, since there would be open currents, so that not only will induction no longer be the variation of the flow of magnetic force in any of the usual senses of the world, but it cannot be represented by the variation of that force whatever it may be. Part 2. Helmholtz theory. I have dwelt upon the consequences of Ampere's theory and on his method of explaining the action of open currents. It is difficult to disregard the paradoxical and artificial character of the propositions to which we are thus led. We feel bound to think it cannot be so. We may imagine that the Helmholtz has been led to look for something else. He rejects the fundamental hypothesis of Ampere, namely that the mutual action of two elements of current reduces to a force along their ion. He admits that an element of current is not acted upon by a single force, but by a force and a couple. And this is what gave rise to the celebrated polemic between Bertrand and Helmholtz. Helmholtz replaces Ampere's hypothesis by the following. Two elements of current always admit of an electrodynamic potential, depending solely upon their position and orientation, and the work of the forces that they exercise one on the other is equal to the variation of this potential. Thus Helmholtz can no more do without hypothesis that Ampere, but at least he does not do so without explicitly announcing it. In the case of closed currents, which alone are accessible to experiment, the two theories agree. In all other cases they differ. In the first place, contrary to what Ampere supposed, the force which seems to act on the movable portion of a closed current is not the same as that acting on the movable portion if it were isolated and if it constituted an open current. Let us return to the circuit C', of which we spoke above, and which was formed by a movable wire sliding on a fixed wire. In the only experiment that can be made, the movable portion B is not isolated, but is part of a closed circuit. When it passes from AB to A'B', the total electrodynamic potential varies for two reasons. First, it has a slight increment because the potential of A'B' with respect to the current C is not the same as that of AB. Secondly, it has a second increment because it must be increased by the potential of the elements A' and B' with respect to C. It is this double increment which represents the work of the force acting upon the portion AB. If, on the contrary, be isolated, the potential would only have the first increment, and this first increment alone would measure the work of the force acting on AB. In the second place, there could be no continuous rotation without sliding contact, and in fact that, as we have seen in the case of closed currents, is an immediate consequence of the existence of an electrodynamic potential. In Faraday's experiment, if the magnet is fixed, and if the part of current external to the magnet runs along a movable wire, that movable wire may undergo continuous rotation. But it does not mean that if the contacts of the wire with the magnet were suppressed and an open current were to run along the wire would still have a movement of continuous rotation. I have just said, in fact, that an isolated element is not acted on in the same way as a movable element, making part of a closed circuit. But there is another difference. The action of a solenoid on a closed current is zero according to experiment and according to the two theories. Its action on an open current would be zero according to Ampere, and it would not be zero according to Helmholtz. From this follows an important consequence. We have given above three definitions of the magnetic force. The third has no meaning here, since an element of current is no longer acted upon by a single force. Nor has the first any meaning. What in fact is a magnetic pole? It is the extremity of an indefinite linear magnet. This magnet may be replaced by an indefinite solenoid. For the definition of magnetic force to have any meaning, the action exercised by an open current on an indefinite solenoid would only depend on the position of the extremity of that solenoid. That is, the action of a closed solenoid is zero. Now we have just seen this is not the case. On the other hand, there is nothing to prevent us from adopting the second definition, which is founded on the measurement of the director couple, which tends to orientate the magnetic needle. But if it is adopted, neither the effects of induction nor electrodynamic effects will depend solely on the distribution of the lines of force in this magnetic field. Part 3. Difficulties raised by these theories. Helmholtz's theory is an advance on that of Ampere. It is necessary, however, that every difficulty should be removed. In both, the name magnetic field has no meaning, or if you give it one by a more or less artificial convention, the ordinary laws so familiar to the electricians no longer apply, and it is thus that the electromotive force induced in a wire is no longer measured by the number of lines of force met by that wire,